In part 5 of AVR ATmega32 timer, we are going to learn timer program to generate square wave. Let us generate square wave of 50% duty cycle on port B.5 using timer 0. Crystal frequency is taken as 8 MHz. 50% duty cycle means on time and off time both are same. Steps to generate square wave are as below. Whichever port pin is given, first of all that pin need to be configured as output pin. We can clear that pin and we can call delay. After calling delay, we can toggle that pin and we can repeat the process. Let us observe in assembly language which kind of step we need to follow. So first of all, we will write our initialization from 0 location. We are going to call subroutine over here in this program. Due to that, we need to initialize stack pointer. To serve the purpose, SPH and SPL register are loaded with the highest location of the RAM. First of all, in main program, we will load R16 register with 20 hex. This will set 5th bit of R16 register. We will also set 5th bit in DDRB register. This will configure PB.5 as an output pin. DDRB register is data direction register. We will load 0 into R17 register and we will use R17 to clear our port B. Once port B is clear, now we can call our delay. From this point, delay subroutine will be called. At the end of subroutine, return instruction is mentioned. Due to that, program will come back to the point and it will execute next instruction. We have used stack pointer. Due to that, at the time of using call instruction, address of next instruction is stored onto stack and return instruction retrieve the same address back and come back to the point from where it was called. Now we will use XOR instruction over here to toggle bit 5 of port B. R17 is loaded with 0. Bit 5 of R16 is 1. If we XOR any data with 1, then that data will toggle. So originally bit 5 in R17 is 0. After execution of this XOR instruction for first time, bit 5 will become 1. Using out port B, R17 instruction, bit 5 of port B will be set now. And the same process will be repeated using RJump instruction. Now, second time when the same routine is being called and XOR is being utilized at that time, R17 bit 5 is already 1, so it will toggle and become 0. The process will repeated and it will be useful to generate square wave. Now let us understand what is written in delay subroutine. In delay subroutine, timer 0 is used. So first of all, we need to load count value into TCNT 0 register. Over here, F2 is selected as count value, which is loaded into count register. Next step, we need to load TCCR 0 register. So in this case, timer 0 is used in normal mode without any prescaler. So we are going to load 01 hex data into TCCR 0 register. Once this data is loaded, timer tick will be started and TCNT 0 register will start counting in upward direction. So now we need to monitor timer overflow flag because the moment TCNT register will reach to FF, it will rolls over and timer overflow flag will be 0. But before that, when we read TIFR register into R20, it will show 0. So, SBRS instruction, that is, whenever timer overflow flag is clear, it will use this jump instruction and repeat the process. But the moment timer overflow flag is set, it will skip this jump instruction and immediately by loading 0 into TCCR register, we can stop the timer. After stopping timer, we can clear this timer overflow flag by writing 1 to TIFR register, and the last instruction is return instruction, so that subroutine can return to the main program from where it was called. In case if we wish to generate 66% or 75% duty cycle, then this toggling mechanism is not going to work, but to serve the purpose, we can set PB.1, because in this case, for port B, first bit is used to generate square wave. We can set that bit. In case of 66% duty cycle, we can call delay twice. After that, we can clear port bit, and again we can call delay routine just once. So, twice we have called delay after setting pin. So, on time will be double than off time. So, due to that, duty cycle will be 66%. In case of 75% duty cycle, we can apply same logic. But over here, after setting bit, we can call delay 3 times. So, that is a 75% of the waveform. And afterwards, we can clear bit and we can call delay once. So, that is the 25% of the waveform. So, this way, we can apply delay routine different amount of time to generate different types of duty cycle. Let us calculate time delay for given program. In this program, PB5 is used as output port. Port B is clear initially. So, this set of instruction that is executed just once at the beginning of program. So, clock cycle count can be omitted for this few instructions. In main program, 4 instructions are there which are working in a loop. This instruction, they are going to consume 7 clock cycle. Usually, any logical instruction, LDI instruction, in and out instruction, they take 1 clock cycle, while call will take 3 clock cycle. Jump instruction will take 2 clock cycle. Branch will take 2 clock if taken and 1 clock if not taken, and return instruction will take 4 clock cycle. So, based on this, number of clock cycle can be calculated for the subroutine, and it is coming out as 17 over here. So, total with main program plus subroutine, total cycles will be 24. We have loaded count as F2 to reach from F2 to FF, and then from FF to 0, it will consume 14 clock cycle. So, inside this subroutine, there is one loop that will get executed 14 times. So, that is the loop when we are looking for timer overflow flag which is being set or not. So, for count equals to F2 value, there will be 14 clock tick, and we can calculate time delay as 14 plus 24 multiplied by 2 into timer clock. We are going to multiply it by 2 because to calculate frequency of oscillation, we need to identify total time, and that is on time plus off time. In case of square wave, it will be same. So that's why we are multiplying by 2. For 8 megahertz crystal frequency, T clock is 0.125 microsecond. That's why in this case, time delay is 9.5 microsecond, which results in frequency of square wave as 105 kilohertz. Now question arises, if we consider any other random value, for example 45 hex, then how many clock tick will be there for 45 hex? We can use equation ff minus count plus 1 to identify how many clock tick will be there. So in this case, 187 clock tick will be there plus 24 clock tick for main program and subroutine other instructions. So if count is 45 hex, time delay will be 52.75 microseconds and frequency of square wave will be 18.95 kilohertz. You can also observe that by loading 45 compared to F2, frequency of oscillation is reduced because in the second case, time period is more. So by using this logic, we can load various count and we can generate various frequency of oscillation. Let us simulate timer program using AVR Studio. At the time of creating project, AVR ATmega32 microcontroller is chosen. Stack pointer is initialized. PB4 is initialized as output. In main program, delay routine is called and PB5 is toggle. In delay routine, timer 0 is used with count F2 hex. We can build this program. You can observe during step debugging, the stack pointer is loaded. PB5 is set, which we can observe over here in this port B. Port B is clear. We are going to call delay. So in delay, timer clock will be used as 8 megahertz because TCCR register that is loaded with 01 hex. So time period for one clock tick will be 0.125 microsecond. TCNT 0 register is loaded with count F2, which you can observe over here in this IO view pen. Timer overflow flag is 0 initially. During this timer loop, in which counting is happening from F2 to upward direction, you can observe that into this TCNT 0 register. Once this count will reach to F, which is reached now, it will become 0 and after that timer overflow flag will be set. Once this timer overflow flag is set, then jump instruction will be skipped and we need to load 00 into TCCR register to stop the timer. After stopping timer, we need to reset timer overflow flag. You can observe it is reset now and now we are going to return to the main program. In main program, PB5 will be toggle. You can observe that now PB5 is set, so it will remain at logic high for the next time delay. For next iteration, same count value is again loaded. By loading TCCR, timer is started. Loop will get executed and timer overflow flag will be set, which is indication that timer rolls over. Stop timer, reset timer overflow flag and return for next round of iteration. We can load this program in Proteus. Proteus simulation is shown over here. In Proteus simulation, on pin number PB5, LED is connected. Pin number 5 of port P is generating square wave. You can observe with this red and blue dot, which is indicating logic high and logic low is generated one by another. LED is showing it's blinking based on whatever data is generated by PB5. Now we have changed count in our timer program. Count is set to 00, so it is counting from 00 to FF. Program is again assembled and hex file, newly generated hex file is loaded over here in this AVR ATmega32 microcontroller. And you can observe that blinking of LED is slow now because delay is more in the counter. So this blink is also, it is showing that state that now time period between two LED on, that is increased. In Proteus simulation, on pin number PB5, digital oscilloscope is connected. We can observe output waveform on this oscilloscope. You can observe digital oscilloscope. Channel A is used, which is generating some waveform. From here, we can change its frequency so that we can identify that it is actually square wave. We can also change its voltage so that we can observe amplitude of this square wave. We can observe time period over here for one cycle is approximately 4 slots, which is going to multiply by 20 microsecond. So we can say it is little less than 80 microsecond. If we calculate time delay, because in this case timer count loaded with 00, so it is going to count from 00 to FF hex and then it will rolls over. So in that case we can approximately find out it as around 70 microsecond, and whichever square wave which is observed in digital oscilloscope, that is also around that, because little less than 4 slot time period is being utilized over here.